Alright, hello world. I'm back. Last time we did... I'm gonna get stuck pretty quickly on 22, but we did... Oh, no, I did 22. It's 23 I'm on now. So, like... We did 21 and 22. 21 is the one that has, like, a cute, quick way of thinking about it. That was basically look at the interval from 0 to n, and if you consider each integer from 1 to n minus 1, when you make a sum that adds up to n, it either includes that integer or it doesn't. Right. So each time you say you do include that point, you get like a finer partition. You get more terms. If you don't include it, you just get bigger, bigger pieces. Basically, you get like two large terms, like n minus 1 and 1. Or if you only selected 1, you'd only have two terms, So that's how you quickly get to the n minus 1 as an answer on that one, on 21. 22 definitely looked at. Yeah. This one's actually not as bad as it looks, because any one of these individually we've talked about before as like the making change example from problem 1. It's yeah, see how it's basically the same as this equation, except you got 1x plus 2y. So the approach is how you would get this generating function in the an case. I wonder if there's... I'll try to look it up. I wonder if there's names for these things. Because, like... I mean, this is not combinations. Well, it kind of is combinations under a certain constraint, right? Anyway, I end up just thinking of them as like, oh, the making change example, and oh, the stamp example is the second case, Bn. And then the third case was like, well, he had weights, which is a pretty good analogy. Like weights summing up to a particular weight. So he has different weights. They're not all distinct necessarily. So you might have like, as soon as you introduce a duplication of a weight, you get multiple ways to do that. And then he had two pans on the scale. So in the first case, he's just talking about weighing them, but in the second case, he's saying you can like counterweight by putting some weight on the right pan instead of the left pan, which is basically like the same exact question, but you're including negative values, including -1. So you're solving equations like this equals some value n, and if you allow the EIs to be 0 or 1, then you get the series we call C. If you include -1, you get a series we call D. And a number of those have been used, not in every single problem, but in a lot of problems going forward, including this one. So 22, you set it up the same way. You do that n times, or n plus 1 times, I guess. And you're sort of summing each of those series, but they're off by 1 each time, so you have to just scale it by zeta. You just multiply by zeta. And anyway, we talked about that last time. So I'm at 23. Total number of non-negative integer solutions to the following equations is less than n plus 2. So we can begin the same way as before and just set this equal to n minus 1. Like this is the n minus first coefficient in front of the series that you get here. And to that we'll add the n minus third coefficient to the series you get here. If we follow the exact method he did last time, we'd get something like anyway, we'll get something like on the first one, x plus 2y equals n minus 1, and then you get 2x plus 3y equals n minus 3, and 3x plus 4y equals, n minus 5, etc. On the first series, you're looking at this, right? On this left-hand side, you're looking at a square and a cube for the zeta. But the catch is we're not actually getting the nth coefficient here, we're getting the n minus first. So what you can do is shift it. We'll just put a zeta times this stuff. This one also, I guess we want 3 zetas to force it to be the nth coefficient. But that's about the extent of my knowledge on this. Yeah, and let's see where he's going to go from there. So I'm going to just take a look at the answer. But I'm supposed to be showing that there's fewer than n plus 2 solutions to this. Let's see if he does something crazy. This was 23. 23. So first of all, he just went with n minus 1 instead of n. So you can remove one of the zetas from my answer. But other than that, sure, he agrees with me. Now, what does it benefit him to not have an extra zeta? I'm not so sure. He then does the telescoping trick again, just like last time. Which I guess I should have seen coming. But yeah, I still don't see the benefit of doing evens. Like here you'd get 1, here you'd get a 2, so it matches up with this. If you do that minus this, yeah, I'm not quite seeing it. It's like this first one is yeah, smaller order. This minus that for v equal to 0, you know? If I look at that, I mean, if you just look at this and you add those, you're going to get, I don't know what he's doing with the missing term. Anyway, of course, you're going to get this, you know, minus that. So the ones cancel, and you get zeta minus zeta squared over the common denominator there. And then the other terms are different. You know, they're different denominators, so we're not going to combine those. Now in our first case we just had a 1 there. In the second case you get different numbers. You have, but in every case you end up with like zeta to the smaller power. So zeta to the v plus 1 over this. So, whatever, it's zeta to the v plus 1 times yada yada. Upstairs you get, of course, zeta v plus 1 minus zeta v plus 2. So why are we able to... Why does he have a minus 1 here? I mean, it should be pretty clear, right? It should be pretty obvious what he's doing. Here's our term in general. He's got a 2 there. Oh yeah, it is a 2. It's even. It was supposed to be odds, so I'm wrong about this. Good. That's not true. It's actually zeta. Yeah, it's always even. These go up by 1, but this is actually 2v. Yeah, I can't do it any other way than express it as 2v. Yeah, here v is 0, here v is 1, etc. V is 2. Yeah, that's closer, that's better. I mean, my initial way had a 2v plus 1, but big deal. So then what? Yeah, I just don't get... Like, if you want it to be telescoping, you're going to have to add something. Last time what he had done was he factored zeta out, and he had 1 minus zeta over this stuff. But he also had specifically zeta to the v plus 1 on top. Or zeta to the v. Excuse me. Like, to show you what I'm talking about, this is what we did last time on the last problem with a nice clean answer. And that one made sense, even though I wouldn't have gotten there immediately. But like when you're used to telescoping series, it's not that complicated. So if you add these, you get what I just said, and you can factor this out. You can factor this guy out. Basically, if you add these, you get an extra factor of zeta and 1 minus zeta, which is why that's there. And then the rest is, the rest just sort of falls out. You do a little shuffling with this series, and you get n plus 1 as a coefficient. On this one, I mean, this is the same. So, of course, we're going to get the same fraction. Like, we still get this. But this time, for some reason, he cancels this guy out and leaves the zeta, which makes sense because we had an extra zeta, I guess. He actually leaves zeta to the v minus 1 in front. So he is dividing by one of them, but he's also got a z to the v, or zeta to the v. That's what I don't really get. Like, it's the same as the previous, sure, except there's an extra zeta to the v on this. So why would this be the same? Never mind. Well, like this part's accurate. If you factor out yeah, I'm not sure what I wrote here, but like I mean this this is accurate too. Other than this part, I don't know why I'm forgetting why I put this here. Oh, that's because that's what I had originally. It would be more like zeta to the 2v, I guess. So his approach. Why? What am I gonna do with a 2v? It's like he's got just a single v instead of a 2. That I'm not getting. Um, yeah. If you look at something like zeta to the 3 minus zeta to the 4. Yeah, sure. I mean, this is also zeta cubed times 1 minus zeta, of course. So that's how you're getting that. But that's not the one that we have there. So like in general, we keep ending up with zeta to the v plus 1 minus zeta to the v plus 2. You can factor zeta to the v plus, well, it's not quite what he does. Oh, he's leaving zeta squared inside. That's probably what's happening. That makes sense, because he wants to leave zeta squared in front of each one of these terms. I don't know why he didn't let it just be odds, but maybe I'll see in a second. So we get that. Or, in other words, zeta squared. This one he accounted for. This one he's leaving inside the series. And this is, you know, what's left inside the series. I'm looking at this chunk right here. So I'm just trying to make sure I can reproduce this series from his answer. The rest of it, I'm sure, falls out without any issues. You know, at 0 you get one of these, so that's where you're getting the second factor, and then you're just taking the limit as it goes off. You'll get a 1, so this times 1. Maybe you don't get, maybe you don't get 1 because this is still there, actually. So you get this term, which doesn't make a lot of sense. Hmm. And he's referring us to chapter 8, which is in the second volume of the book. Alright. This is what I had gotten up top here. He instead said, let's look at the n-1 coefficient, and we'll just get rid of one of these. So he had instead this series. This is now 4 instead of 5. And this is 3 and 4, etc. So yeah, he's just restating this junk with the even powers, and that's what he's got written there. So I follow him up to there. After this, he's doing this telescoping junk, which I'm still not used to for some reason. But, you know, for instance, this one term you could write as this if you want. The problem is, well, anyway, when you add these fractions, you're going to get this denominator minus that denominator in the numerator. So 1 minus this minus 1 minus this. So the 1's cancel, and you end up with a positive zeta minus zeta squared over, right? I just wrote this up here somewhere. Over the common denominator, right? Which you can factor, but what's he, like, we didn't actually start with this. Well, no, we do. For this first term we do. But in general, we have this guy right here. So whatever I do here, I mean, it's sort of like we've got a zeta to the 0 floating around on the top that I don't want to ignore. But anyway, you can factor this out. I see that he factored one of them out. We've got an extra zeta, and then you've got your... Right, then you've got what we started with, this term, or this term right here. So you're kind of always going to be able to do that, right? Like when I got here, I'm able to factor out, like, I don't know why I'm having such a problem with this. Yeah, just factor out zeta to the v, and you're left with a zeta minus zeta squared. So if you want, you can factor out zeta to the v plus 1 instead, and then you're left with 1 minus zeta. So the only difference between this and the previous question was that there's an extra even power of zeta sitting here. So that's our numerator. This is just that part without the even power. Why wouldn't he also divide by A to the V, I just don't quite see it. Alright, this cannot be that complicated. If you add these, you get, I'm looking at this chunk again. If you add these fractions, you'll get zeta to the v plus 1 minus zeta to the v plus 2. You get this bottom denominator minus this first denominator. The double negatives cancel, make this positive. That's where that came from. Okay? That's what you get in the numerator. Downstairs we get this same stuff that we've been looking at the whole time. It's this form, so maybe I won't even bother writing that, but you get the product of those two denominators. Then he's got this extra guy, zeta to the v minus 1 times these things. And then he's also got, he's dividing by 1 minus zeta outside, okay? The 1 minus zeta I can see is going to cancel, because this factors. So like, upstairs now we have zeta to the v minus 1. You could factor zeta to the v out, right? Ah, there's the 2v, okay. And then you get, well, one of them, sure, there's still one there, minus zeta squared. And we're dividing by 1 minus zeta. So, anyway, these cancel and leave you with a, you know, and the other two terms are there. The other two factors are there. This cancels and leaves you with a zeta. So I'm getting zeta to the v minus 1, zeta to the v plus 1 with the 2, you know, common denominator downstairs. So there's your 2v that I was looking for. And oh, and the other one just cancels. Why did this magically work out? And I guess there's really no difference. Like, I had a 1 and a 3 and a 5. You could do the same thing, but my formula would have had, like, if I want this extra 1 on top, like a plus 1, I'm just going to also introduce it in the bottom. So my formula would have had an extra 1 over zeta out front, like this one did back in the previous problem. Mine would have looked like that. So I should have gotten this along with this extra term, zeta v minus 1. Although, again, I was looking for the nth term, but I guess that comes up in a second. That won't be relevant until the next line. Oof. I still have a hard time going from here to there. There's no way I would get this answer again, even though I just saw it last time. If you give me the answer, I can verify that it's the series that we're trying to find. But anyway, I mean, it's pretty obvious though, right? If you have two factors here like this, of course you can do this telescoping thing. They keep being off by 1. It keeps like adds 1, adds 1. So that's why you're getting a difference of 1 here. So it's not that, it's actually kind of a calc 2 thing. Anyway, we're doing a lot of juggling here with the zetas out front. Anyway, I clearly buy that. This is what we were looking for. So he's not wrong. How do you get to here? Right, this I have not verified yet. So these still... Oh no, they don't cancel, because this wasn't here before. It's not really a regular telescoping series. This thing screws it up. This extra factor. Hey! So yeah, it's not telescoping. I can't do what I was hoping to do. Well, if it's not telescoping, what do you do with it? How did it get here? Anyway, it's clearly not telescoping. But I'm at least happy up to here. And this tau v represents the number of divisors of v. This I'm not familiar with, but it must be, it looks like it must be a pretty basic number theory thing. Yeah, sadly I'm not gonna get that one. We were supposed to be showing that the solutions to this handful of equations has fewer than n plus 2 solutions. I guess there's also still a, oh, that's all he did. Okay, I see. He just took out the first term, right? He must have rewritten it though. Huh. Like this first term is, you get this guy. But then when you start writing out terms, the very first one is just 1 over zeta times like 1 over 1 minus zeta minus 1 over 1 minus zeta squared. Then if you want, you can do the rest of them. Sure, but you don't need to do this division. We left it there. So I don't know. For now, I'll leave it out front. But anyway, you're starting at 1, going on. You get this junk, with our telescope. Well, thing that looks like a telescoping, but it's not because of this factor out front. V plus 2, V plus 1. Like that. So this mess I should make some sense of. If you multiply these, you get like a whole quadratic looking thing. So that's not what he did. Oh, wait a minute. You could make this plus 2 if you want, and you can put this out front like that. Oops. And then because ordinarily when you add these, which we've done like 3 times today, you get this. So if I scale it by v plus 2, how does that help anybody? We just get, 2v plus 3 and 2v plus 4. Anyway, So you got 1 minus zeta to the v downstairs in this chunk. Like, clearly this is supposed to be... Well, I'm forgetting about this guy, too. This gets distributed in. So if you were to, like... yeah, right. If you multiply this, we say we get here. If you divide by 1 minus zeta, you end up with... Right, it cancels this part. Right? So here I get zeta to the 2v, this stuff, just from this first part, sorry, the part in parentheses. The numerator will be this. Well, that's not quite true, because I adjusted this guy. Okay. So... Anyway, this part alone would have given you zeta to the v plus 1 minus zeta to the v plus 2 in the numerator. And there's an extra zeta to the v plus 2 floating around. But this screws up my denominator. It's, again, the product of these two things, which we don't want. We end up with like 1 minus zeta to v. So I'm kind of lost there. Not seeing what I'm doing here. But anyway, there's an extra 1 minus zeta in the denominator that I was going to forget about. So that's in here. And if you put 1 over zeta cubed, you get what we had a moment ago. So I just adjusted this part. So my question now is, like, how does this equal zeta to the v over 1 minus zeta to the v? I guess it's conceivable. Maybe. I don't see it. I was gonna let this cancel, and then so like zeta, or really factor zeta to the v out, and you get zeta. So if you factor this part out, you get zeta to the v plus 2, zeta to the v plus 1 times this guy. So they finally cancel. And then I got our stupid product that I'm not a big fan of. And this is zeta to the 2v plus 3. Or, you know, zeta to the v times an extra zeta to the v plus 3. Like that. Which is actually taking sort of care of there with the 3. No, it isn't. Well, if you brought it in, it would cancel and you get 2v back, which makes sense because that's where we started. So yeah, this denominator, I don't see the point of multiplying it out, but I guess I could try. It's 1, you know, minus 2 gross 2v plus 3, and then plus zeta to the wait a minute, how did I manage to... I see, it's not 2, sorry, I screwed that up. This is what the term is over there, plus zeta 2v plus 3. In the middle you have 2 subtractions. You have just minus one of these and minus one of these. Which definitely does not help me. I thought maybe if I expanded this, it would like clean up somehow. If I just did 1 minus zeta times this, it would like look better. But it doesn't. If you did this minus zeta times itself, I mean, you still get this extra zeta term. You get minus this to the 4. I guess one of these cancels. That's about it. So don't expand it. Man, I'm almost done with this problem. I'm like right here. I'm just trying to get from there to there. I'm just trying to see why. I'm okay with this. I'm okay with this whole formula. I'm trying to see why this is evidently equal to zeta squared, 1 minus zeta squared, and then over here we have 1 over zeta cubed times a sum from 1 to infinity of zeta to the v over 1 minus zeta. So I'm trying to confirm that. And then I can move on once I figure that out. Sadly, I'm going to have to run in like 10 minutes, so. This book was going a lot faster a few days ago, but that's alright. It's a bit of a slog here. It'll stop being a slog in a minute. I'm on 23. 24 is going to be similar, but like I've done the first handful of these before, at least up through 30. I did a handful of these too. So like I know it gets a little better. But yeah, anyway. Dying trying to do 22 or 23, I guess. It was total number of these solutions is less than n plus 2, and then he says the difference is equal to the number of divisors of n plus 2. So I was looking at number 23 today. 24 is very similar. Your numbers have changed, of course, but at least they're squares. And 25, I don't recall being this much of a nightmare. Anyway, back to it. So the answer was solved by Cesaro, solved by Catalan in 1880. Anyway, we expanded this thing. I pretty much got the same thing for the series, but then I never see these telescoping tricks. It's not really telescoping this time because there's an extra factor. But anyway, it kind of looks like a telescoping thing. So I'm okay with the left-hand side of this, like as an answer to the question. You would then be asking like, okay, what's the coefficient of, I guess n minus 1 in this case, the n minus first coefficient of the series expansion of this. Which you don't have to actually do out. His follow-up observation here, the last sentence of the answer, makes no sense to me, but he's referring to like a much later chapter in the book for an explanation. Also, it looks like it looks pretty fundamental. I just don't know it because I'm like not great at number theory. So I don't get that line, but that's okay. That's just something else that I should probably read up on. But yeah, what's driving me crazy is I'm trying to get from here to there. Once I get that, I'm happy with this answer. And I had thought that, just look at the first term, because he started the series over at 1. But for some reason, it's not going very well for me. So what do we really get when you look at just the first term, just the v equals 0 term, you're getting two of these. You get, half of this part right here. You get this from that and that, and then you get this one term like this. Okay? Then the rest of the series is there. It looks like this, with our little telescoping chunk that is not quite telescoping because this is there. So I agree with this. I buy that. There's a 2 there. This is somehow, I don't know why I'm not seeing it. I mean, I guess you could factor an extra 1 minus zeta out, right? I feel kind of dirty doing that, but sure. What's wrong with that? So you get a zeta, you get a 1 minus zeta squared, 1 minus zeta squared like that. And then here we just get a 1, and here you'll get 1 plus zeta. Oh, okay. I'm an idiot? No, because the denominator now is just 1 plus zeta. It's not zeta. Upstairs you'll get, zeta. So this chunk is zeta over 1 plus zeta. I don't get it. That's not what I was supposed to. I thought we were going to get this. This isn't the same as 1 over zeta. I don't get it. Anyway, it's okay that I don't get it because it wasn't necessarily going to work out like that. There could be some sort of like shifting of the indices to make it look like this. But still, I just kind of was hoping that this would be term 1. So yeah, if you did multiply that, you get what? 1 minus zeta squared, right? Which he doesn't have here, so I think that's the wrong direction. Oh, right, looks good. Yeah, I'm just not getting this. What the hell? I'm just trying to see here to there. Yeah, no, it's fine. Here to there. Because this I effectively got this as the answer. But then he jumps here and then he has to discuss this series to tell you the answer. Which is fine. I'd be okay with that too, because it's just like a gap in my knowledge that v should be the divisors of v. I mean, I can look that up. It sounds familiar in number theory, but it's been a long time. But yeah, this is the more basic part. Why is this series equal to this one? Yeah, this first term really did not do anything I was hoping it would do. So if I hadn't done our little trick, of course, it gives you another way to think of this term is 1 minus zeta, zeta minus zeta squared over the common denominator, which I've been doing again and again today. Basically undoing what he did to get to this answer. So, of course, if you divide by this, you get a 1 on top, which is pointless. That's where the answer came from. This is actually what we started with. So like when I was answering this question, this is what I wrote down first. And then we got to here and eventually get to this series. It's really got to be something kind of obvious. I don't understand why I'm having such a hard time with it. You could kick this one out. You could just get zeta to the v on top, sure. Is it two series and that's why I'm having such a... Oh. No. Is it maybe two series? That would be really silly if that's all it is. There's like an extra zeta right there. I would feel pretty dumb if that was what it was, huh? Do you think that this is the first term, and this is the second term? That would be hilarious. Anyway, again, this starts at 0. If you want to make these match up, you get exactly this. You get 2 factors of zeta, but it doesn't telescope or whatever, so I don't see why you'd get a solid term there. But anyway, at least we're doing something different. So if I want these to match up, I can just factor, it's the same as saying this, zeta squared 1 minus zeta, oops, and then here you get zeta to the v plus 1 over 1 minus zeta to the v plus 1, which, that's basically just a geometric series, right? It's like if you had, well, I realize it's not geometric at all. But that formula without the series there, without the sum, that would have been like a shifted geometric series. I guess that's not the direction he was going. Anyway, so like these terms look like zeta over 1 minus zeta plus zeta square over 1 minus zeta square, etc. Yikes. So you could now write this as like a double sum, but why you would do that, I don't know. Like this is zeta plus zeta square plus yada yada. And the second one is the same idea, but you do powers of 2. You do multiples of 2, zeta 4, zeta 6, etc. The zeta squared on top just shifts it, so you're not starting at 1. But these are geometric series right here. But I'm summing all those up. So like this chunk is this stuff with higher powers and stuff. That might actually have, if I knew it a little better, that would probably explain the divisors thing. But anyway, I don't want to go there right now. And then here, if you want to make it match up, you would just factor 2 of them out, or 1, 2, 3 of them out, which he has as part of his answer. But then what? So does this chunk really just equal, is this equal to 1 over 1 minus zeta? And this part, if we factor out 3 of these, which he left out front, you get basically the same series we were just looking at. Oh, well, you basically get what he wrote. At 0 you get 2. Huh. So is there an extra term here? At 0 you get 2. He wants me to get 1. So maybe if I subtract that one term, suddenly that will... I don't think so, though. So there's an extra term here. You know, there's the zeta cubed, there's the 1 minus zeta thing. And then I'm saying we could maybe split this up. So if you plug in 0, you get zeta squared over 1 minus zeta squared minus, and then you get more or less what he wrote. From 1 to infinity, just zeta to the v, right? So I removed the 0 case, and I left a 1, which gives you zeta to the 3, damn it. How did I mess that up? Yeah, no, I definitely messed it up. So there's like an extra term. His has an extra term for some reason. So maybe he what? Yeah, his starts at 1. Mine started at 2 for sure. That's weird. But they're being subtracted. Well, today was not very enlightening. Alright, so fine with that, evidently. I mean, I went a different track. I started just splitting this series up, which you can't even really do unless you know it's, if you know it's convergent, then I guess it's fine. But I think it would, does that even make sense? You can't just split up alternating series like that. It's not alternating, I'm just saying you can't just take a series of like an minus bn and say that it's this. But I'm saying you can if it's convergent. It would have to be, I feel like it would have to be, that doesn't make sense. You just can't do that. You just can't do that. Right? That would mean things like this, I mean, like that. That would mean this is convergent, right? Like that converges, so clearly we can just split it up. It's infinity minus infinity. No, no, no. Which means this whole attack that I'm doing has to be wrong. Like this, the past 10 minutes of me trying to split it up into 2, that makes no sense. Just sort of fundamentally. Which is a shame, because I thought I had something going there. But that's wrong. That's not true. It feels kind of true, doesn't it? But this is like Calc 2 stuff. That's just not true. I mean, okay. It's probably true under conditions like these are absolutely convergent series. These two. The pieces that you're splitting up. Then I would buy it. So maybe it's not so crazy after all. But man, why is this question so brutal? This is really not that hard. We're going from here to here. he doesn't even explain it because it's just algebra, right? So it's got to be pretty straightforward. And this almost matches up. Like if I kick 2 zetas out, you get exactly this on the first term. This is that. So I'm just off by, like, what is going on? Anyway, if you're out there watching me and you joined a little late, what I'm looking at is start over from scratch a little bit. I'm looking at 23. 22 is not, well, okay, yeah, 22 was a little gory, but it wasn't nearly this bad. I just had one little issue with the answer in 23 that's making me like spin my wheels for the past 45 minutes. Other than that, they're actually very similar. So 22 says, there we go. 22 says, find the total number of basically natural number solutions, although you can include 0, so non-negative integer solutions of the following equations. So it's not a system. They're saying find all the solutions of this, as well as these, as well as these. You know, it's not like it's a simultaneous situation. They're just saying, like, how many solutions would there be to this mess? And that alone, if you're not already familiar with it, that would be a big headache. But this equation is extremely similar to basically the first problem that we did, where you're like, how many ways can you make change for $1? And you say, like, okay, if this is pennies, nickels, dimes, etc., we come up with a way, like we basically came up with a function that counts that. And in that case, it would be like the series 1 plus zeta squared plus zeta cubed, etc. That geometric series represents the pennies. And then 1 plus zeta to the 5th plus zeta to the 10th plus zeta to the 15, etc. That series, that geometric series, represents the nickels. And you do this 5 times. So the rational function that generates these solutions is given by the product of those geometric series. Okay? So when you get something like this, just this first equation, sorry, you can't see it, this first equation, if you're trying to find the number of solutions to something like this, you can look at the series 1 plus zeta squared, yada yada. Anyway, whatever. You basically look at this series times this series. Since that's a 2, I'll put a 2 here. If you were to expand this, the coefficients would give you these answers, the number of solutions to this equation. So like the nth coefficient in this expansion would be the answer that you're looking for. So we're doing a series of these. We're doing a bunch of them. We're doing, this is the one I just wrote down. You just do it again and again, and you add up all those series. Okay? And that's how you get an answer like this mess. This series plus this series plus this series. He did some shifting so that instead of looking for the n minus first coefficient, he multiplied by zeta so that we're always looking for the nth coefficient. But other than that, that was basically it. He did that, and then he did like some cleverness here to get this formula. But that one was doable. Because it happens to be telescoping, it sort of simplifies to be this, and you get an answer. So that was 22. We did that last time. And then today I've just been stuck on 23 because it's almost the same question, but we've got some power up top. So I was able to follow them up to here. It's like this, basically the same as last time. I'm able to get this part. This gory answer. And then, you know, the answer would be like, oh, the coefficient of the nth coefficient of this expansion would be the solution. So he talks about that down here, but my big issue was like, how does he get from here to there? You know, he simplifies this formula to become this formula, and then he's able to talk about this chunk, and then we're done with the problem. But for some damn reason, I guess I'm just an idiot. And then I tried to split this series up into two, but that's a little silly. So yeah, just trying to get from here to there. But I'm documenting everything that I'm doing, so you get to see me struggle with this. Now if we like add these fractions, you sort of go backwards. You sort of get where we came from. So that's why I'm not doing that very often. I tried like looking that as the zero term and maybe adding those fractions, and I thought I'd get this out, but that is not what happened. Yeah, that's it. That's our series. It starts at 0. So I'm trying to show that this equals these two terms at the bottom. Well, one of them is a whole series. So it's almost, I thought like, oh, maybe he just kicked one term out and then rearranged some stuff and got this, but which is probably still true. I just didn't see it yet. All right, so then you get zeta to the v. This is v starting from 1 this time. 1 over, or sorry, zeta to the v minus 1 minus zeta to the v, like that. And then he's able to talk about that series. Oops, yeah, that series. Which is something I don't understand, but that's okay. That I'm happy to just say, well, I'm not really super familiar with that part. But this part is clearly algebra, right? This part is not that complicated. Plus, it's sort of fundamental that you get there, because that's the answer. Once you can look at this part, you can say, oh, this particular coefficient. But if you can't get there, then I guess you can't do it, right? So what the hell? So yeah, I thought I would just try one more time here. That's basically all I've been doing for the past almost hour. Well, yeah, 45 minutes, an hour, something like that. Is trying to get here. Yeah, I really don't want to split that up into two. It seemed pretty clever at the time, but you can't do that in general with series. So I feel pretty dirty saying, oh, it's this minus that. Kind of. I have to look that up too. I'm a little rusty on whether that would ever be true. If they're individually convergent, then yeah, that's probably true. But otherwise, absolutely not. And that's kind of the point of various series questions, is that if you subtract something, it converges, but if you don't, then it doesn't. Anyway, thinking out loud. So what are you going to do with this? Is it some... no. I was going to say, maybe it's some sort of like like a summation by parts thing. I mean, without this, what would we get? We'd get a telescoping thing that looks like 1 over 1 minus zeta. And then this part just goes to 1, so I guess just minus 1. I think it's some sort of like Abel summation by parts trick, which I'm also super rusty on. No, I'm pretty sure he would have said that. It's got to be simpler than that. But I noticed if I factor 3 out, then this matches this, right? You basically, this almost pops out immediately once you factor zeta cubed out of this part. It's a plus right there. Alright, I mean, if we just do this like blindly again, you get, here's the first term, and then you get one of these guys. And if you want, you can rewrite this as zeta minus zeta squared, but I promise that doesn't help. Zeta minus zeta squared over these two things. So it's basically 1? Really? The first term is 1? What? Okay, sure. I guess so. Oh, no, it's not. Sorry, I forgot the denominator. Good, good, good. So the first term is 1 over the product of these two things. I'll keep going. But you also get, when you add these two, you get a denominator that I was about to ignore. Oops, you get that. So, sure, these cancel, but you get this stuff. And then also, we have the rest of the series. So now we're starting at 1 instead. If you want, we could factor zeta cubed out, right? And then this matches, so we get like zeta to the v plus 2. It matches this guy on the right. So far this is the same, this left-hand side equals this junk that I wrote out. But this, I mean, that's not that, first of all. So this, pulling off the first term, I mean, it doesn't seem to give me this, that's for sure. And even if it did, what about this mess? Well, clearly I'm going to have to give up for one day. I'm going to take off in about 5 minutes. I'm being defeated by this one line. But if we skip ahead, you'll see the tone really changes. Like 24 is potentially kind of a similar thing. Not really. Not really. It's a similar question, and yeah, I don't know. It has kind of a different flavor than the answer to 23. But 25 seems to be just switching gears. It's not the same. I mean, I realize in general it's the same. Like this, we've been doing this for like the past week, but um, yeah, you can see it. The rest of the problems are not nearly as nasty as this one particular chunk getting from here to here. So if I ignore this, it's not the end of the world. It's not going to affect the next handful of problems. But yeah, it'd be nice if I could still do algebra. I don't know what's going on here. I brought this in. It would be v minus 2. Oh, no, I'm confused. Why did I think this matched up? Because it does. This was here. This was actually part of the answer that we had. This whole left-hand side was correct as far as I can tell. Right, so that's why I pulled this out. This is still the left-hand side. Do this 3 times, you get, this guy becomes that. Eesh. Spinning my wheels. I mean, what else can we do with it besides... And where does this first term come from? Anyway, what's frustrating me also is this is not telescoping. That would have been cool, but because of this factor, you can't just start canceling terms as you add them up, you know? That would be awesome, but that is not what happens because of this stupid zeta that's in the way. So that guy keeps increasing by 1. You know, so anyway, you see what I'm saying. You don't get this minus that. The terms don't just cancel as you move on. Which is fine. So what? What happens then? Anyway, like I was saying, I'm going to feel real stupid if all he did was this series minus this series. That didn't seem to work out for me, but... But it almost looks like it, right? If you factor out a square, it matches with this first term. That's the square, right? So if it was true that I should write this nowhere because it's the wrong thought, but if it were the case that this equaled this, then we'd be all set. This time the v starts at 0, I guess. But that's not true. I mean, anyway, that would explain the first term. But that's not true as far as I know. This is this. Or, put a v there if you want. These are equal. This is not. So yeah, sorry we're not making a lot of progress today, ladies and gents. I think I will not spend another session looking at this one. So next time I'll go a little faster through 24, 25. I'll figure this out on my own. If I do figure it out, I'll mention it at the beginning of a video, but yeah, I'm not expecting that to happen. I shouldn't be expecting this to be true. That would be crazy. I mean, wouldn't that effectively mean this is that? So, no. That's not going to work. I don't think that z to the k is the same as z to the k plus 1 over 1 minus z to the k plus 1. That would be crazy. That would be madness. Yeah. This is a good place for these notes because this doesn't make any damn sense what you're saying. Good. This does not equal that. I'm glad we're in agreement. So yeah, this is stupid. What does that tell me? Well, I guess that tells me trying to factor this out to sort of mush this together to be that is not the right approach. Because it's just not true. Alright, good. So forget about that. Thanks for the follows, people. Captain Blacksmith and Instucky. Thank you for the follow. Yeah, I'll disappear in a minute. Should probably just disappear now. Yeah, what am I going to do with this guy? It's just obvious, right? It has to be obvious. He just says this equals that. But I'm pretty sure if it was like a technique, he would have said something. So I'm just staring at this answer, I guess. This top line. I guess I'm staring at this part. Like, if we multiply through by zeta cubed, right? Is it any more obvious that that should equal this? If we knew that, we would be done. And if I multiply through by this squared, right? Is it more obvious that this is true? Ugh. I don't think it's helping. But these are alternative forms of the same statement, right? So this left-hand side is, of course, itself minus zeta times this, so this gets increased to v plus 3. I don't see that helping us. But yeah, these are both the same statement, apparently. I guess I could divide by zeta, divide everything by zeta, and add this, and you get something equal to 1. Great. But yeah, I'm definitely getting away from it with this. Alright. This is what the terms look like. Eesh. Right, yeah, I just don't see it. If you did want to write these terms out, of course, they look like so at 0 you get gross 1 over zeta 1 over 1 minus zeta minus 1 over 1 minus zeta squared. Then you get just 1. This one's 1 over 1 minus zeta squared minus 1 over 1 minus zeta cubed. Then you finally start getting positive powers of zeta. I don't know why I put it up there. Zeta times 1 over 1 minus zeta cubed minus 1 over 1 minus zeta to the 4. Zeta squared times 1 over 1 minus zeta to the 4. 1 minus zeta to the 5. Yada yada. That's the left-hand side. I don't think that helps anybody. Yeah, it really looks like he just took the first term off. Sort of. Maybe not. Could have taken like a couple terms off for all I know. I mean, here he like clearly divided by 3 so that it would match that, I guess. If we pull zeta cubed out of this, you get zeta v plus 2. And we're saying that's v plus 2 over this minus zeta to the v plus 2 over this. That's what's inside the series. Another way to have thought about it is leave that. And then this is what I was saying not to do, because it sort of undoes our work, but it's also the same as this. Zeta to the v plus 1 minus zeta to the v plus 2. In general. So you could factor zeta to the v out, but I don't see how that's helping us. Kind of just gives us back the original stuff. Alright, so here you get zeta minus zeta squared. So if you let 2 of these come in and cancel, I could see how you might get to here. Or really, you could even let these cancel. Anyway, this is what we started with. So this is stupid. This is where it came from. This was the original series that we had. So we went from here to this left-hand side. And I'm trying to get from there to here. Alright, this session is going on for way too long. I'll stab at this again tonight on my own. But if I make any progress, I'll make a quick note of it. And then tomorrow or next week, tomorrow or like Monday, I'll move on to 24. Hopefully 24, 25. And then we can get back into some flow here. Yeah, because the answers are going to change a little bit more going forward. They're not going to look quite like this series. Anyway, you have a magnificent day. Hope you have more success than I did. Great to see you all. Arrivederci.